Good afternoon, everyone. I'd like to thank you all to be here today. It's really a pleasure. I'm super excited to welcome you guys to this data governance session. We are going to explain how we are using system tables and lineage information for dynamic tag propagation. So I'm Pedro Teixeira. I'm the head of data platform at iFood. And I have here with me.
I'm Lucas Carson, a staff data engineer at iFood.
Okay, so the data platform teams take care of everything that people use for analytical purpose, and data governance, it's also something that we are responsible for. So before I start talking about data governance, I'd like to take 2 steps back and introduce you guys to iFood. So iFood is a Brazilian tech company, and we are not only a delivery company, we are pioneers in Brazil to connect people to meals and to create this very seamless customer experience. So with more than 110 million orders per month, we are the leaders in Brazil, and we connect millions of monthly users to drivers, to business partners, and we operate across all regions in Brazil. Actually, data is at the heart of everything that we do. So data will fuel innovation, will fuel products, and how we create this ecosystem, connecting deliveries, drivers, customers, and restaurants, grocery stores, pet shops, and so on, you name it. To give a better perspective of how many data we handle on a daily basis, we have more than 150 proprietary AI models, resulting in 14 billion real-time predictions, which makes our delivery routes better, will reduce errors, and create this excellent user experience. We have a 16 petabytes of data lake. We have more than 15,000 tables in our Unity Catalog. We do a lot of retraining. We have more than 1,000 retraining and model updates per month. In Brazil, we are the top, one of the top consumers, Databricks consumers. We have more than 800,000 machine hours processing data per month, and we are already observing a huge impact of AI in our revenue. So we estimate about 30% of EBITDA impact only by AI. So to dive a little more into our data governance topic, which is very important to us because this needs to work within our rules. We have a lot of guidelines and policies that people need to conform to. I'd like to pass to Lucas Carson to explain why we did the dynamic tag propagation.
Thank you, Pedro. So the object of this session today is to explain a little bit how we can use the lineage and privilege tables in Unity Catalog system tables. And we'll talk a little bit about reactive and proactive security strategies and how we can ensure transparency, and also about how we can identify who can access which kind of sensitive data, even for confidential data. So also how we can audit and do monitoring and classifying the tables, sensitive tables in the downstream. So data governance is a big challenge for us, I guess, for every company. And also because it's hard to track who can access sensitive data and what kind of permissions these users can have. So if you imagine it, if you have a big team with thousands of users using, accessing data with a lot of autonomy to also for read the data, but also for write their own data sets. So if you have one single core team to do that, it's impossible to scale this. So it's important to share those kind of responsibilities. So data classification is easy to be automated with PII data, but it's very hard to do that with confidential data. And I will explain a little bit more in the next slides. And also because, for example, due to this kind of this level of autonomy that the users have, it's sometimes the users forget to set the appropriate tags for the tables. And it's difficult also to track the confidential and sensitive data in downstream. And also, when you have more than one workspace, the lineage view that you have in Databricks, they don't match the lineage between different workspaces. So each workspace has their own view of the lineage. So for that, what are system tables in the catalog? So system tables basically are delta sharing tables hosted by Databricks. And for our solution that we're going to present today, we use these those important tables. So the lineage table is to track the downstream, and the privilege tables to identify who can access which kind of sensitive data, and their privileges and everything related, and also the tag tables to, in a way, to label the classification of PII and etc. So here so system tables are a Databricks hosted analytical store of your accounts operational data found in the system catalog, and system tables can be used for historical observability across your account. This is the Databricks documentation. So at first, let's talk about proposed workflow for tag propagation. At first, we need to enrich the data, normalizing it, simplifying it, and enrich to then process that. So this diagram represents an overview of our DLT pipeline. So as you can see, first we have the table lineage here. We ingest the table lineage and we split in two DLT views, one called matched lineage and another unmatched lineage. The first one is where both source and destinations are in the same row, and unmatched lineage I will explain better after. And then we can merge them together back, join with the table tags from system tables. Then we have the output table called lineage. With this output table, we can split into other DLT tables, one called edges and vertices, to use for our graph processing. Also, the lineage table we can use to control the offset that we use to next iterations to passing as start timestamp to do the ingestion incrementally. And also, we have this another step. Here we have the skin API. And with that, we can load and generate an output table called user groups that I will explain in the next slides. So at first, we need to ingest the lineage system table incrementally using rich data chain feed. And system tables in general supports rich chain feed natively, but we have some limitations. In this case, we needed to ingest the data using batches, because if we try to ingest the tables with streaming and rich chain feed configuration, this can limit us in how we need to aggregate the unmatched lineage block, and also to avoid, for example, having a big we have a big watermark session. So to do that and to better scale this solution, we have this limitation, so we need to do in batches. And also, in DLT pipeline, the Python API doesn't support batch reading in Lineage table because it's a delta shared table, and we need in this case to use the SQL API table chains that does the same effect. And then we need to ingest the scheme users, groups, service principals to rule the scheme API. But I will explain better. So at first, to normalize and simplify the table lineage ingestion, at first we need to identify some dirty data that we can have in this table. For example, the prefix of S3A, S3N, etc. And also some informations that are not useful for us. For example, partitions and etc. So as you can see in here, we have S3 prefixes. Oh, come on. We have S3 prefixes and partitions with timestamp information that are not useful for us. So for the lineage view block, the first block that I show in the diagram, at first we need also to filter out irrelevant data where entity type is dashboard or null because they are not useful as well. Then we need to apply coalesce and in the source table full name column and the source path column to simplify merging them in a single one column that we can call a source, and do the same for the target. So we can have less data to, we can make our graph processing easier. So also we need to use, we can regex patterns to remove dirty data like file names, date formats, hashes, etc. And we can replace with a placeholder. And as I said before, we can normalize path schemes. And then we need to remove rows where source and destination are equal to avoid cyclic lineage in your graph, and then deduplicate the data. So as you can see here, we have the S3 prefix normalized, and the DT timestamps replaced with a placeholder that we call it DT. And it can be anything else. So for a matched lineage view, the second block that I show in the diagram, at iFood, in our task orchestrator, we have 8-hour timeout policy, so jobs must run before reach 8 hours. So to better track potential lineage breaches, for example, when the users read some data set and then collect them to the memory and then transform back to data frame and write in another place, we can try to track the indirect lineages, for example, where we know that are the same notebook or the same job reading and generating that data. So in this case, we need to filter only when one of the fields, source or destination, is empty and the other is filled. And then we can group them with the entity's primary key. For example, workspace ID, the entity type ID that can represent job or notebook, etc. And then we can group with the session window, Spark function with a session duration of 9 hours, 8 hours from our 8-hour timeout policy, and plus 1 hour for have a margin of safety. So here it's possible to understand better how we can group those kind of events. So as you can see, the first two rows here have all the same information of job, ID, etc. Oh. And as you can see, source is filling in the first row, and destination is filling only in the second. And we have less than 9 hours of difference on event time, so they are the same session window and the same job, but they are unrelated. So we can group them together. The third one row is alone, so it's not useful for us to identify who is what is the origin, the source of this table C. And the last two rows are the same case of the first, but we have another entity ID, another run ID. So we have, even with, we have the same timestamp, but in this case is another job, but they are, those both rows are in the same session. So this is an example of our DLT pipeline, like the diagram that I showed before. So at first we need to consume for user groups, in order to have the user groups table, the output table, we need to consume the skin API, listing the users and service principals. Then we can collect those data in memory and convert back to data frame. Also, we can have a harded column type to identify if it's a user or service principal, only because they are in the same table, and like the entity type and the entity ID. But in this case, we have some limitations, because the skin API on account level returns empty for the groups field. So it's necessary to use the skin API on workspace level. So if you have more than one workspace, you need to iterate through the skin API on every workspace that you have. So here an example of the user group DLT pipeline. And this was the user info table contains the relationship between the users and groups, even when the groups are inherited, it's not direct. And also, we use this table after to do the monitoring, to do the alerts and everything else. So this is an example of the output. Here we have the hard-coded column to identify the type. We have the name and the email and group information, and if it's direct or indirect. So then we need to, we have, with the data normalized and simplified, we can go to process the data. And we need to generate the edges and vertex tables. And then we can load them in GraphX with a custom pre-gel computation. So in this diagram, it represents some overview of the GraphX processing. This is not a DLT pipeline, it's a job pipeline. So we have the lineage, vertices, and the edges. We use as input of GraphX, then we do a pre-gel calculation here, collect the vertices, and then we save as final table, call it table classification. So here is how we can do the tag propagation and how it works. In this case, for example, imagine that you have only the A, D, and G nodes tagged with some kind of tag called PII or something similar. So in this case, A is PII, D is public, and G is confidential. So in this case, every other everything else is not classified. So we can infer that C nodes and B nodes and B node are PII because A is PII. Also, the E node is public because D also is public. And in this case, F is generated from C and E. But in this case, PII is more relevant than public. So F node will be public as well. And here, the last node is generated from PII and confidential classifications. But PII is more relevant than confidential, so we classify as PII. So to do that, at least we need to have the first table in the lineage in downstream tagged. So if you can tag the source table, you can do that. And we have a lot of ways to tag tables in Unity Catalog. Doing it manually or tagging through some automation using a PII auto-discover tool. But tools like any kind of auto-discover tools like Databricks Warehouse Monitoring, Presidio, Macy, they work well for PII data, but they don't work well for confidential data because this kind of data, they don't follow patterns. So the rule is the classification of the confidential is more related to the business. So also how we can handle in cases that we have the table secured. For example, the users set a mask function, for example, in the table. So we can create another tag called, for example, security, and classify this table as manually as public. So as you can see, the I node is confidential and the J node is public. And in this case, the K node was treated. And because of that, we can consider that L is not anymore reading a confidential data, so the lineage is truncated here, and the L node will be public as well because it's not using the confidential anymore. So about PRGL algorithm, it's a platform for parallel processing of large-scale graphs, and was developed by Google, and it's used to calculate page rank. And then we have a lot of advantages using GraphX, like scalability, simplicity, and efficiency. So about the PRGL algorithm has some phases, like the initialization, where each vertex starts with initial value, or and then they receive and update the vertex message. Then they send the message to next neighbors, and then the iteration that is repeated until a convergence condition is met. So those are the GraphX PRGL parameters. This is from the project's documentation, the GraphX documentation. And also, but this is important to mention that edge direction that controls how messages flow between the nodes. In this case, we are using the out mode. And the vprog is, I guess, is the core function that we have because this function will update the vertex state. So the workflow works like this. We have the initialization. So at first, the vertex will receive the initial message value. The vprog applies the first update. The iteration, then the send message function will pass the message through the neighbors. And then the merge message will combine those messages. for each vertex, and vprog will update again the state based on received message. Then we have a stop condition when no more messages are sent or the maximum numbers of iterations is reached. So this is an example of code that we did. So it's important to notice that here we can have a if clause where the message sensitive has an order, and the question that I showed about the relevance between PII and confidential and public can be treated here. So this is the most important part of the code. So also here is the send message function. The if is important also here because when we need to not send the messages to next nodes, we can use the iterator imp to stop the propagation. And here at the merge message, if the source message from the parent node is more relevant than the target node, so we can keep the most relevant message, and if else, we not. So this is an example of the output table that we have. As you can see, we have the catalog, schema, table name, and also we have a column called data classification that we will have the label of the table here. Also about a column called security. For example, when we treated the table with a masking function, for example, this security will be true. And now about monitoring and how we can do monitoring with that output table. So in this case, we have reactive strategies and proactive strategies of security. Sorry. And reactive security focuses on responding to true and mitigating threats after they occur. And proactive emphasizes prevent threats before they happen. So we can use both strategies to handle to do our monitoring above the table that we generated. So with users inf table, we have the relationship between users and groups. And also with the privilege tables, we can track which kind of table of permission the users have in their tables. So with that, we can generate alerts. We can tag back the tables. We can use tools like DiscoverX from Databricks to tag tables back. We can revoke grants, and we can apply masking. And also, it can be used with a back feature that Databricks is releasing. So this is an example of the alert on the Slack. We are only generating alerts, but we are not revoking automatically. So with that, the user can take some action. So also it's possible to track open issues. We can do this extra table, for example. With the table privilege, we can identify if an user has access and which kind of privilege the user have in that table. If doesn't match our rules or our defined rules, we can track the status as open security issue, or for example. So why this is important? So this allows us to scale the company, avoiding having PII or confidential data open to the users and providing more autonomy to users. And it's important to emphasize that because confidential data doesn't work with the auto-discover PII tools. So because business users will set that this kind of data is confidential or not. So with that, we can create a sense of responsibility among users because it can serve as a form of education. For example, if users receive alerts, they can learn about the concern of having PII and of having confidential data exposed to the company. So we can reduce risks and problems when are detected, applying masking automatically or maybe revoking access in reactive security way. So also we can generate audit reports for privacy teams or for some other purpose. So to finish, we have some takeaways and recommendations. If you need to users not create downstream tables, for example, they don't need to have the autonomy to read PII data or confidential data. It's important to create a PII workspace with catalog binded in read-only mode. So they can read the tables, but they can't write in another place. So it's important to mention that Lineage table from system tables has a retention of 1 year. And also, the first Lineage history ingestion might be heavy, and then in this case, you need to use a bigger computational cluster to process that. And after, you can decrease the size of the cluster or even use the serverless. So also, because we run in batches, you can adjust the job schedule as you need. And also because currently serverless jobs don't support Scala. So libraries like GraphX and GeoGraph frames are not supported because they are created in Scala. So to use and process with GraphX, you need to mix them. And thank you, everybody. Feel free to reach us at LinkedIn.
Muito bom.